Let's take a look at another schema, the labeled set schema or XBLOG schema. And again, this is another one that we proved in the last lecture using singularity analysis. So it says if you've got a construction of the form f equals set with some restrictions of g, and if it's XBLOG, that means that g can be approximated as something like log of 1 over 1 minus z plus a constant with other constants alpha and beta involved. So if you have that approximation of g, then taking e to that power, which is what the set's supposed to do, gives you a good approximation of f, and then you can extract coefficients from the standard scale using f. And again, there's a lot of detail to proving this fact involving the singularity analysis process. But once it's proven, then we can apply it easily in lots of applications. And also there's a corollary that immediately gives the average number of components in a random object, where it's alpha log n, where alpha is the coefficient of the log in the approximation. So that's again a transfer theorem from the last lecture, and now we're going to look at applications. And the first one is, again, we'll just be focusing on the coefficient asymptotics. First application is all about cycles and permutations, and again, just to refresh memories or for people who didn't see the last lecture, we'll take a look at this one. And we also not just interested maybe in permutations, but how many cycles are there on average in a random permutation. And we looked at this problem. We've looked at this problem as an example all the way back through part 1 of analytic combinatorics. But now we're going to show how this problem and variants of this problem and problems like it are immediately handled with a general schema. So our construction is a permutation is a set of cycles. So that immediately translates to e log of 1 minus e for the cycles, e to that power for the sets, XBLOG. So that form of the generating function says we're going to use the XBLOG theorem. So now it's what we want to do is calculate the alpha, rho, and beta, but those are immediate because in this case it's not approximation. The thing that's raised to the e's raised to that power is log of 1 over 1 minus z. So that's alpha equals 1, beta equals 0, there's nothing added on, and rho equals 1. So we just plug in alpha equals 1, gamma of 1 is 1, beta equals 0, so that's a 1, rho equals 1, so it's 1 to the n, and all that's left is 1 from XBLOG. So coefficient of z to the n of p of z is asymptotic to 1, and it's exponential, so number of permutations asymptotic to n factorial. That doesn't seem like much of much interest, but remember the corollary says the expected number of components, so that's the expected number of cycles, which does maybe require some calculation. It's alpha log n, alpha is 1, so that's immediate through singularity analysis proof that not just the number of permutations, but also the average number of components comes immediately log n. And again, for a basic problem like this, we have lots of ways to proceed to prove the log n result. Our point is that for variants of this structure or for other similar structures, we can use precisely the same process to get an answer where direct calculations might be extremely complicated or prohibitive. So like examples, so we looked at derangements, so we can look at derangements, or we can look at a problem like how many cycles are there in a random derangement. Might be hard to think about how to even approach a problem like that, but it's immediate from the XBLOG schema. And precisely the same process works for in more general settings. Like maybe we want to know about cycles in derangements. We talked about derangements, which are the set of all permutations having no singleton cycles. So take out the singleton cycles. So that's the construction. It's a set of cycles, none of which are length, or all of which are length greater than 1, greater than 0. And so all we do is subtract off 1 from log of 1 minus z to take out the singleton cycles. D of z equals x log 1 minus z minus 1. That's x log. The only difference is that now that beta is minus 1. So that's the x log form, it's just that beta is minus 1. So when we now apply the theorem, we get the same answer, except that because of the e to the beta, we get e to the minus 1. And that's a familiar result. The number of derangements have to multiply by n factorial. It's n factorial over e. And when we looked at this as an early example in part 1 of the course, and that 1 over e started out as a finite sum, and we had to show that the tail is negligible and so forth. This higher level way of looking at the same problem really gives insight in where this form of the solution comes from. It's all about the minus 1. We subtracted off the minus 1. That translated right through the theorem down to the exponent of e. And not only that, we have the corollary to the theorem, which tells us the average number of cycles in a random derangement. It's still log n. It doesn't involve beta. So the average number of cycles in a random derangement is proportional to log n still. And this generalizes to include any restrictions on the cycle lengths. So you could pick t different integers and say, I want to study the class of all permutations having no cycles of length w1, w2 down through wt. The construction is just sets of cycles with that restriction on the cycle lengths. Immediately translates to a generating function equation where we subtract off the term corresponding to each one of those cycle lengths from log of 1 over 1 minus z. But when applying the x log theorem, all that does is when we approximate that function near the singularity, which is rho equals 1, those z to the w's become 1, it all comes to the beta. So applying the theorem, then we're just going to get e to the minus beta. And then again, it's just e to that constant. And whatever those constraints are, you can compute the constant and you can know that the number of generalized derangements of that form are n factorial over e to that constant, very easy to compute. You pick 2, 3, 5, 9, and 11, and you can compute the number and know the average number of derangements that don't have cycles of length 2, 3, 5, 11. You might be challenged to try to derive a result like that using elementary techniques. And also, the corollary still holds. Average number of cycles in such a permutation is still proportionate to log n. T is a constant. We're only disallowing a constant number of cycles, essentially. But we could also, with singularity analysis, using a version of the theorem that carries more terms, derive more terms. These can be carried out to arbitrary asymptotic accuracy without any problem at all. So again, that's what we always strive for in analytic combinatorics. Take a construction, take it to the generating function, get the coefficient asymptotics immediately. Let's look at a much more complicated problem to deal with. This is called the two regular graphs. It's actually not at all more complicated through analytic combinatorics. So these are undirected graphs where all the nodes are degree 2. So every node of degree 2 essentially means it has to be a little circle. There's only one two regular graph of size 3. It's a little triangle. And there's only one way to label that one. It's not any different. So that's like down there is at the right is the representation of the graph as a set of edges. If we have an edge from 1 to 2, an edge from 1 to 3, an edge from 2 to 3, then all the nodes have degree 2. and that's the only possibility. For 4-node graphs, to keep all nodes of degree 2, it's got to be a little circle, but now there's a bunch of different ways to label it and get different graphs. So in this case, there's 3 different edge sets. So you fix one of the nodes and do the permutations, but then you have to remove the flips. So either order counts the same in this type of graph because the set of edges won't see the difference how you draw it. And so for 5, it turns out that there's 12. Again, fix one, there's 24 permutations, and each one appears twice in both its orientations. For 6 now, you could have the 6-node graph, and again, 60 ways to label that, or you could have 2 3-node graphs, and that would work fine. So there's actually 70 different 6-node graphs. That's with sets of 1, 2, 3, 4, 5, 6 edges that every node has degree 2. There's 70 of them. So that's, and for 7 nodes, there's 465. And as we get more, we can have different combinations of the little ones. So it's a set of subgraphs, of components of this type, and then n-1 factorial, or k-1 factorial over 2 ways to label it if there's k of them. And so you could work with elementary methods to try and count these. But with analytic combinatorics, it's actually quite easy. You also might want to know the number of components in a random 2-regular graph. So this one, there's 1 component for 60 of them, and there's 2 components for 10 of them, so that's an average of 1.143. And for this, it's 1.226. Maybe in some application in chemistry or some physical process, you might have a situation where you have a random structure of this type and you want to know the number of components. That's the kind of problem that we're getting at with this kind of analysis. So let's look at it from the standpoint of analytic combinatorics. And you can find more detail on this in the books in these indicated pages. So what is a 2-regular graph? It's a set of undirected cycles of 3 or more nodes. That's all. That's actually a fairly compact specification of what it is. That immediately translates to the generating function equation. It's half. Undirected cycle means you take half. That's the same as when each graph appears twice. And then again, we have to subtract off the small ones. Z over 2 and z squared over 4. That's the class of 2-regular graphs. Now that looks a bit complicated at first until you realize that it's X-log form. So X-log form, all it says is that what's raised with the e to the power, what's in that power is some constant times log of 1 over minus z times some constant plus some other constant. It's asymptotic to that near the singularity closest to the origin. Singularity closest to the origin is 1. Near that, we have beta equals 3/4. We have alpha equals 1/2. That's the coefficient of the log. We have rho equals 1. Immediately, now we can apply the theorem. Beta is 3/4, so we have e to the 3/4. Alpha equals 1/2, so we have gamma of 1/2. And that's it. So immediately, the X-log theorem translates from the generating function equation to the coefficient asymptotics, e to the minus 3/4 over square root of pi n. And so if you want to get the number of 2-regular graphs, you multiply that by n factorial. A very general theorem when we're using the set construction, the X-log theorem, to get coefficient asymptotics. And this type of asymptotics would be quite difficult to get using normal techniques. Now again, underlying this theorem is singularity analysis, so there's quite a bit of mechanics under there, but when it comes to applying, it's no problem. And again, the component corollary applies here. Now we have alpha equals a half, so average number of components in a random two regular graph of size n is half log n. Very easy to get results of this type using the X-log schema. So that's our second example of a widely applicable schema that's based on singularity analysis.